Alright, the goal tonight is to go over a little bit of trade mathematics. It's going to be very basic math, nothing too complicated, simple stuff. I'm not going to go over how to add, subtract, multiply, or divide. If you need that, go find a math tutor. But we're going to go over some basic math that we're going to need to know for this year. So, it's mostly simple stuff. The first thing we'll do is area. Area is important because we're going to be learning a lot about load calculations and things like that. So you need to be able to find an area of basic shapes. So area is pretty simple, right? Area is going to be length times width, width times height, whatever. So if we have a rectangle is going to be, say we have 12 inches, and then let's add another dimension to it. We'll add another dimension and say it's something simple. Let's say it's 10 inches, right? So we have 12 inches by 10 inches. 12 inches by 10 inches, obviously, we have our calculator. 10 times 12 is, 10 times 12, 120 inches. Very simple. Not going to go over it much further than that. But if you need the area of a basic rectangle, width times height, done. Now, a circle. For the area of a circle, you got to know the radius. So, if we have a basic circle, then you have the diameter. So say we're talking about a 12-inch duct, right? 12-inch duct, 12 inches is the diameter. We take half of that to get the radius. So half of 12 will be 6 inches, right? So pi times radius squared. Normally what I do is I simplify that to pi times r times r. So if you have a calculator that has pi in it, you can throw pi in. But for the most part, 3.14 is fine for most of the math that we do. 3.14 times 6 times 6 give you 113. So that's the simplest way. That's 113 square inches. Yeah. So pi times r is the simplest way to do the area of a circle, but it's pi r squared basically. Triangles. You don't need triangles very often. You're not going to have many triangular shaped rooms. You will have pyramids and stuff though, so it's good to know the basics of it. But if you need to do the area of a triangle, then you got a simple triangle. Say it's 12 inches by, let's go 8 inches. So our formula for a triangle is base times height divided by 2. So bringing back up our calculator, our base is 12. Our height was 8. Get that number, divide by 2. Area is 48 inches. Again, pretty simple. If you need any more practice with that, simply draw some circles, draw some triangles, come up with some basic areas, and see if you can remember these formulas. The the rectangle and the circle, you probably want to know like the back of your hand, basically. The triangle is not so important. You can look it up if you got to. Look it up on this piece of paper, which I'll put up so that you guys can download it. But both of those are real important to be able to do. Volume. Volume just adds a third dimension to everything. So, if we have a duct, we need to know the length of that duct. We have a cylinder like a water heater. We'll need to know the height of that cylinder. So basically all of these are just adding height into the equation. The pyramid's a little different. With that, we're adding the height and dividing by 3 instead of dividing by 2. But for the most part, all these are just area measurements with another dimension added to them. So if we have a cube, like a room or something like that, and let's just make it a straight up square room. So 20, go feet this time. Let's go 20 feet by 20 feet by 8 feet tall. So we have 20 times 20 times 8. Simple enough, right? 20 times 20 times 8. 3,200 cubic feet of area in the room. Cylinders. Again, pi r squared, or pi times r times the height of the cylinder. So if this cylinder was, say, 22 inches wide, we're talking about something like a water heater. 22 inches wide would have an 11-inch radius. So we have 11 inches. It's 60 inches tall. Say it's 60 inches tall. 11 times 11 times 3.14 times 60. So 11 times 11 times 3.14 times 60, 22,796 cubic inches of room. Engineer's rule to architect's rule. We're going to skip now. Come back to, oh no, we didn't do the pyramid. All right, so cylinder, pi times r times height. Let's go to the pyramid real quick. All right, so for a pyramid, we need to know the 3 dimensions of it. So say we have, just go 10 inches. Normally this would be something like a vaulted ceiling or something like that, but we'll just go with a more basic measurement for now. Let's just go 10 inches by 10 inches. By 12 inches on the height. So we'll have 10 times 10 times 12 divided by 3. Base length by base width times height. So 10 times 10 times 12 divided by 3, 400 cubic inches of room in that pyramid. As I said before, let's skip engineer to architect's rule. I want to come back to that. For now, let's go square inches to square feet. So if you have this rectangle, 12 inches by 10 inches, especially if we're dealing with ducts, when we get into CFM, most of the time we're going to have to be taking that area of the duct and we have to convert it to square feet instead of square inches because our measurements are cubic feet per minute. They're not cubic inches per minute. So we have to know the area of the duct in feet to be able to calculate other things with that duct, mostly CFM. So if we need to do that, we get this 12 by 10 duct. We need to know the area in feet before we can do anything else with the measurement. We have to use the same unit of measurement for the entire process, right? So when we need to know that, we just take the measurement we get, because we always talk about duct in inches. We don't talk about it in what size it is in feet, right? We're not going to say 1 foot by 0.83 feet or something like that. We're going to say it's 12 by 10. And then our answer, and take that answer and divide it by 144 to get square foot of duct, square foot of room in the duct. So 120 square inch duct is 0.833 feet. Then we can take that measurement and do whatever else we need to with it. Cubic inches to cubic feet doesn't come up very often, but in case you need to do it, if you had a room, we can go back to that other room we made over here. Say we had these measurements in inches. So 20 feet would be 288 inches, right? (20 feet, 288 inches, 8 feet, 96 inches. So that's the measurement we had. We did all our measurements in inches for some reason. We go 288. Wait, did I mess that up? I think that messed that up, right? So 12 times 20 would not be 288. That'd be 240. Let's fix that. (240) 240 by 240 by 96. Make sure I didn't mess up the other measurement. Nope. So 240 by 240 by 96. 5,529,600 square or cubic inches. Divide that by 1728. And we'll be back to our 3,200 cubic feet of room. So that is cubic inches to cubic feet. Again, both of these are just constants. You'll want to try to memorize them if you can. It's especially important that you memorize square inches to square feet. Cubic inches to cubic feet's not quite as important, but they're both relatively important. Equivalent diameter of duct is another one I want to save for a minute when we go to Excel calculators. I want to do some exercises in Excel here shortly on engineers to architect rule, and then talk about equivalent diameter of duct for a minute. CFM. CFM, if you know the velocity of that's inside the duct, which a lot of times we're going to be targeting velocity, but if somehow you know the velocity or the velocity pressure in a duct, we can calculate CFM by the area of duct in feet times velocity. Conversely, if you know the CFM running through the duct, you can divide that by the area of the duct in feet and find velocity. So the first one we're going to talk about a lot later this year when we talk about sizing duct and finding proper duct sizes using velocity, because that's a really efficient way to do it instead of using in a ductilator. But for now, say you want to know the approximate velocity in a duct. Just as a quick aside, a kind of look ahead, maximum velocity in a supply air duct is 900 feet per minute. Absolutely no more than that. You never want to go over 900 feet per minute basically in a supply air duct on a trunk line. That is ACA's maximum recommended velocity. So, say we have this 12 by 10 duct and it's the trunk of a 2-ton system. All right. So, if we're doing 400 CFM per ton, all right, if you don't know, we'll go over it multiple times again later, but 400 CFM per ton is a good middle ground for airflow on the system. So 400 CFM per ton on a 2-ton system would be 800 CFM, right? If a 12 by 10 duct was our trunk, so we had a 12 by 10 duct as our trunk, that would be 120 square inches, right? We do that again, divide by 144.833 square foot of duct. If we take that 800 and divide it by 0.833, so again, what we're doing is we're finding this area of the duct in feet, and we can find the velocity if we divide the CFM by the area in feet. So that 800 CFM divided by 0.833, all right? We do that 960 feet per minute. We will learn a lot about this equation, but for the most part, well, as a basic understanding for now, understand that basically that 12 by 10 duct is too small for a 2-ton system, which hopefully everybody would realize that anyway. It's a little small, but that's a quick way to figure out, okay, if I want to know the velocity in my duct, how can I find it? If you know the approximate CFM you're running, then you can divide it by the duct area in feet, and you will get velocity in duct. So we'll go over that a ton. So just keep that in mind. For now, that's kind of just a look ahead, but I want to make sure you have that equation sitting there so you are able to use it. All right, finding CFM using the heat rise method. This is another thing we're going to talk about some more, but I want to give you a basic look ahead on, right? So if you want to find CFM on a system and you have no way to measure it, you're absolutely got no other tools with you other than a thermometer, and you're trying to figure out, okay, how many CFM is this system putting out? This does not work for cooling. I repeat, do not try this in cooling. This does not work. You will not know the BTU output in cooling without a lot of information on the system. And even then, you're going to be stabbing at it unless you have, your psychrometers hooked up and all that stuff, and you're finding total enthalpy and all that stuff. But for heating, it's really simple because we're not dealing with latent heat or anything like that. We're just dealing with sensible heat. So, say I have an 80,000 BTU, 80% furnace. Okay, so if I have an 80,000 BTU, 80% furnace, I need to know the BTU output. The BTU output of an 80% furnace is going to be 80% of 80,000 BTUs. So if we take 80,000, multiply that by 0.8 because it's 80% efficient, we're going to get 64,000. So just remember, just multiply by your efficiency with a decimal in front of the number. So 80% multiplied by 0.8, 92% multiplied by 0.92, 95% multiplied by 0.95, so on. So our BTU output of this 80% furnace would be 64,000 BTUs. CFM equals BTU output divided by 1.08 times delta T. Delta T is our temperature difference. Hopefully you guys know this by now, but delta T is going to be your temperature difference across the furnace. 1.08 is just a constant for air. Sometimes you'll see this written as CFM equals BTU output divided by 1.1 times delta T. Some people just round up this 1.08 actually because it's not that critical of a number, but the right number is closer to 1.08. So going back, if we have a 64,000 BTU output furnace, and say we measure the return air and the supply air, and we get a 50-degree temperature difference, 70 degrees to 130 degrees. We get 130 degrees on the supply, 70 degrees on the return, no, 120 degrees. 50-degree temp difference would be 120 degrees on the supply, 70 degrees on the return. So you got a 50-degree temperature difference. You got your BTU output. Generally, how I do this is you get two options, right? You got a calculator that can do it. We can do 64,000 times 64,000 times parentheses 1.0 crap. Clear that out. 64,000 divided by parentheses 1.08 times our 50-degree temp difference. Would be 54, right? Equals 1,185 CFM. If you can't input parentheses in your calculator, if you just got a basic calculator, then the easiest thing to do is do 1.08 times delta T first. Whatever your answer is, BTU output divided by that. So again, 1.08 times our 50-degree temp difference was 54. So 64,000 divided by 54. 1,185. As another example, you had 100,000 BTU furnace. So 100,000 BTU, 90%. So let's say times 0.9, 90%, 100,000 BTU furnace would be 90,000 BTUs output. If we had 75 on the return and 130 on the supply. So 130 on the supply minus our 75 on the return give us a 55-degree delta T. So we've got most of our numbers now, right? We got 55-degree delta T. We got a 90,000 BTU output. So our 55 degrees times 1.08 is 59.4. Clear that out. Remember the number, 59.4. 90,000 divided by 59.4 would give us 1,515 CFM. Now, a critical part to remember if you're doing that is if you're trying to figure out the CFM when it kicks into cooling, then you need to make sure that fan's on high speed and not low speed for the furnace. So if you're going to bother doing it, you might as well check what your CFM is on low speed, furnace speed, and then check what the CFM is on high speed for cooling, just so you know what the two numbers are. You might as well take them both. But typically, you're more worried about that delta T on a furnace. So When we talk about troubleshooting furnaces, they're going to have a minimum and a maximum delta T so that you don't do any damage to the heat exchanger or anything like that. But if you need to know the CFM for cooling, you can stick that fan on, run it in cooling speed, then take the heat rise across the furnace, and you can determine CFM that way, and it's pretty accurate. So it's a quick method of doing it. If you're dealing with the heat pump, you need to convert watts to BTUs because you have, say, a 10 kW electric heater kit. Again, you don't really want to be doing this with the refrigeration side of the system because it's not going to output a constant amount of heat. You're not going to know how much heat that heat pump's putting out because it's going to be dependent on outdoor temperature. So what you want to do is you want to just use the electric heat only, turn it into emergency heat, take your kilowatts and convert them to BTUs, and then we can use this heat rise formula again. So, as an example, we had a 10 kW heater kit. We put it in emergency heat, put the fan on a heat pump. It usually runs in single speed anyway, so it doesn't matter, but you have your fan on and you run that 10 kW heat kit in emergency heat. 10 times 3.414. You'll also see it written as 3.412, 3.413. They're all really close. It doesn't matter. So 10 times 3.414. Wait, no, I've got this written backwards. What the heck? All right, so let's fix this formula real quick because it's kW times 3414 or watts times 3.414. Because that would not be a 34.14 BTU heat kit. So let's just do this real quick. I'll make sure I fix this. Let's do this. Watts times 3.414 or kW times 3414. All right, and I'm going to fix this so it covers that up. All right, so try this again. Now with our fixed method here, watts times 3.414, kW times 3414. So kW again, 10 kW times 3414, 34,140 BTUs. So 10 kW heat kit is at 34,140 BTUs. 1.08 times our delta T. Say we put our temperature on the return, we get 70. Put it on the supply, get 100. So 100 supply minus our 70 return gives us a 30-degree delta T. 30-degree delta T times 1.08, 32.4. So our 34,140 divided by 32.4 gives us 1,053 CFM. You want to see that the other way, we can do it again. Say it's 10 kW, 3414, 3440 times, put in parentheses, 1.08 times 30-degree delta T, 1000, no, 34,140 divided, not multiplied, times 1.08 times our delta T. There you go. 1053 again. 1053 CFM. So the heat rise method is a good way to determine CFM if you've got no other methods around. Because it basically also it requires is looking at the data on the equipment and using a thermometer. It's a quick way to find CFM. We will practice this a few more times, so don't worry if you don't have it right out of the bat, right out of the gate. But it's a simple way to find CFM. And watts to BTUs is always going to be important. There's always going to be a time when you need to know the BTU output of something that's electric. So watts times 3.414 or kW times 3414. Atmospheric pressure. Atmospheric pressure is important primarily because sometimes we need to know absolute pressure and not gauge pressure. So you need to remember what atmospheric pressure is. Hopefully you guys know this by now, but if not, remember atmospheric pressure is 14.7 psi or 14.696. It's not going to be very common, especially in our area where you need to know actual atmospheric pressure. This is usually going to get you close enough on what you have to do. If you're doing a job up 2,000 feet above sea level, you might want to go and actually look up what the atmospheric pressure is going to be at that elevation, because obviously it changes as the elevation changes. We deal mostly in Virginia. Virginia is mostly close enough to sea level that just using 14.7 or 14.696 is going to be plenty close enough for you to do it. So, if you're doing a test on a system and you pump that system up to 450 psi, the pressure exerted in that system is actually 464.7 psi. And that's important if you're doing something with gas pressure laws or anything like that. So that's a quick primer on that. In case you need to know any of these other numbers, feet ahead's important. We're going to talk about feet ahead a lot when we get into boilers and things like that. 33.9 feet ahead is atmospheric pressure. You get above 34 feet ahead and you can't siphon something up higher than that, because atmospheric pressure, it drops below atmospheric basically. That's the only real reason you need to know that. That's more of a plumbing thing than an HVAC thing, but that'll let you convert PSI to feet ahead. We'll talk about other ways to go from PSI to feet ahead or inches of water column later. But for now, I just want you to know what atmospheric pressure is in case you got to do PSIG stuff. Capacitor formula under load. I mainly put this here so that it's a quick reference. We're going to talk about using this formula when we talk about troubleshooting individual components. But if you've never done it before, you can run a capacitor under load. You can take the amperage and take the voltage at the capacitor itself, and you can determine what the actual rating is of the capacitor that way, instead of pulling it off and turning your meter to capacitance and using your wires. So again, another thing we'll do more practice on, but it's a nice, I throw it in my trade math sheet just so I've got it sitting somewhere, because it's something that's kind of a pain in the butt to find sometimes. Google search will usually turn it up, but but most of the ways that it turns up aren't easy to take a look at. Um, so anyway, capacitor formula under load I throw on this sheet just so I've got it essentially. But if you need to know the microfarads of a capacitor and you want to know what they are running, and depending on who you talk to, taking that measurement while it's running is better than taking the measurement with it out. Generally, I'll do it both ways if I suspect a fail or weak capacitor, but it doesn't really matter. Take the amperage at the capacitor. So say the amperage of the compressor, your H terminal on the capacitor. You need to take the amps at that location. All right. You need to multiply that by 2650, and then you need to divide that by the voltage measured across the capacitor. Do not assume that if you have a 240 volt compressor that you're going to get 240 volts across the capacitor. If you've never done this before, then you may not know this, but your voltage at your capacitor is going to be a reasonable amount higher than your voltage coming into your unit. So say our compressor is pulling 5 amps, right? We'll use the parentheses here to make this a little easier the first time. So say we got this compressor pulling 5 amps. We're going to multiply that by 2650. Again, you're going to measure the amperage at the terminal that's on the capacitor, not on your incoming wire, just your wire going to your compressor, because if you pick the wrong one, you might get a slightly different reading. But at the Herm terminal, we stick our amp clamp around that wire, we get 5 amps times 2650. And we're going to divide that in a realistic voltage you might get. Remember, capacitors are rated for 370 and 440 volts. The reason they're rated for those voltages is because you actually see them. So a realistic voltage here might be 345. That would be a 38 microfarad capacitor. So those are two relatively realistic readings. You could have a 40 microfarad capacitor. You'd be reading 38.4. Generally, plus or minus 10% is fine. So this would be within spec. I know most capacitors say plus or minus 6%. That is the rating that it's allowed to be as it leaves the factory, but generally plus or minus 10% is still fine for operational purposes. So 38.4 is pretty good. So that would be how you use that formula. And again, we'll practice that at least one more time when we talk about testing individual system components. Ohm's law. We're not going to go over Ohm's law right now. It's in here. E equals I times R, or volts equals amperage times resistance. You should know most of this by now, but we'll talk about troubleshooting electrical stuff and we'll go over that. But it's nice just to have Ohm's law sitting there. If you don't remember it, there's your quick look ahead on Ohm's law. E equals I times R. You might want to Google that a little bit and refresh yourself because it's something you're going to need to know in the trade a lot. Gas pressure law. This is kind of important, especially as we work on higher pressures, testing systems at higher pressures. Here's a common misconception. A common misconception is that nitrogen does not change pressure with temperature. This is wrong. Every gas will change pressure with temperature. Now, nitrogen changes less with temperature than some other gases might, but it's still going to change pressure with temperature. So, especially if you're doing a VRF system that you're testing at 550 psi and you're doing it at those weird times of the year where one day it's 80 degrees and the next day it's like 50 degrees. All right. If you've got that situation, your pressure drops. It's 80 degrees, you put the test on, it's 550 psi. You come back the next day and it's 30 degrees cooler and the pressure dropped. And you think, well, nitrogen doesn't change pressure with temperature, so I got a leak. No. That's not what's necessarily going on. You need to determine whether or not you actually have a leak. So, this is how you do it. This right here is how you make sure whether or not you have a leak or your pressure just changed with temperature. So this one's going to take a little bit, it's going to take a few more steps. All right. So gas pressure law is your final pressure, your P2. So the pressure you have the second day. So the pressure that it changed to. P2 equals P1. So the pressure you started with times T2, which is the pressure you ended with. So the pressure on the second day divided by T1, the temperature on the first day. So that sounds complicated. Let's just start writing some stuff down so we can see what's going on. So, as a matter of fact, let's take this and move it over here. Oh, nope, wrong button. It's odd. Let me do it this way. Just a second. All right. So our gas pressure law is P2 equals P1 times T2 divided by T1. So let's go back to our example. We had a VRF system. All right. Move this up here. So something to work with. All right. So we had a VRF system, and the pressure we had on the first day, we put it on test the first day, is at 550 psi. Then that day, the temperature, our T1, was 80 degrees. The next day, we come back. Say our pressure dropped to 520, so P2, say we dropped to 520 psi. Temperature that day is 50 degrees. Let's see how this turns out. It's just a random example. But, all right, so 550 psi the first day, 80 degrees outside, 80 degrees Fahrenheit, 520 psi the next day, and it was at 50 degrees Fahrenheit. First thing we have to do is we have to use absolute temperature. That means we need to add so that temperature in Fahrenheit is absolute, which would be Rankine. All right, and we need to have absolute pressure, so we have to add 14.7 psi to both of these. So our P1 would not be 550 psi, it would be 550 plus 459.7. So let's do that. 550 plus 459.7, because remember, there's no such thing as cold unless it's at negative 460 degrees. So whatever. Oh, we're doing that to our pressure, not our temperature. Try this again. First, let's do the pressure. Do the pressure 550 psi plus 14.7. Give us, plus 564.7 is our absolute pressure. And then to our 80 degrees, we will add 459.7 degrees. So we have to add to our 80 degrees outside. It was not 80 degrees. There was not 80 degrees worth of heat energy. There was 80 degrees of heat energy plus our baseline of 459.67 to get to 0 degrees Fahrenheit, right? Because 0 degrees Fahrenheit isn't actually nothing. 0 degrees Rankine is nothing, and that's negative 459.67. So add those together, we get 539.67 degrees. 464.7 psia, absolute, because we have to add atmospheric pressure to it, just like we talked about earlier. Now we do the same thing with P2. P2 was not 520, it was 534.7. And then T2 is not 50 degrees. It's going to be 50 plus 459 points. So it's a lot of steps, but it's important, because otherwise your number is going to come out way crazy and it's not going to work. So now we have our absolute pressures and our absolute temperature, psia. And now we take those and we will do our formula. So we take the formula over here and we plug these numbers in. So P2, 534.7 should equal P1 564.7 times T2 509.67 divided by T1, which was 539.67. We'll go ahead and add in our parentheses. So if these numbers in the formula do not come out to this number, we know that we have a leak. So let's just give that a shot. 564.7. Let's add our parentheses here just to make sure. 564.7 multiplied by 509.67 divided by 539.67. We should have gotten 533 psi. What would you know? We got 534.7. So maybe your gauge isn't reading as accurately as it should, but you are actually higher than that number, so you could confidently know that you don't actually have a leak on that system. if anything, your pressure went up a little bit. And over the course of that day, you were good. So this absolutely works with nitrogen, absolutely works with any gas that you're working with. As those temperatures change, those pressures will change. If you want to be able to predict what your pressure should have been as the temperature changed, that's how you do it. Now, I know there's a lot of steps in this process, right? So if you have to, go back, watch it again. I'll give you guys some practice on it. If you got questions, let me know. We can do a couple more examples, but that's how the gas pressure law works. So now that we have that, let's switch to Excel. What we're going to do in a second is we're going to switch to Excel. We're going to talk about engineer to architect's rule, and we're going to talk about equivalent diameter. And the reason we're going to switch to Excel is what I want to do is I want to show you how to put some of these formulas in Excel, and maybe we'll even throw the absolute pressure formula in there. I want to show you how to do that so you can use Excel or Google Sheets to make some of these processes a lot easier. Especially Google Sheets. I tested it before I started this recording, and you can do it mobile so that you can use these before. I've done it with Excel too. With Excel, it's generally easier if you're going to do it in mobile to set up all your formulas first at home on your computer, download the sheet, then you can change the couple variables and get other numbers. I do it with a lot of the more complicated equations so that I got things on standby and I can double check I've got everything right. But with Google Sheets, you can even throw in some pretty complex formulas. If you got a good calculator, you can do it in the calculator if you got the formula sitting by, but it's way easier to just set it up so you can plug in a couple numbers. So let's switch to Excel real quick. And let's talk about putting some formulas in Excel. So the equivalent diameter of duct, that is 1.3 times width times height to the power of, so we have to, I'm just going to write it as if you would the Excel formula for now so you can see it. If you look at the formula, right? So if we switch back for a second, let me do this. We switch back and we look at the formula again. So we're looking at the formula for equivalent diameter of a duct. It's 1.3 times width times height to the power of 0.625 divided by width plus height to the power of 0.25. Both of these are exponents, right? Just like r squared, you have to have an exponent there. These are weird exponents, and you're never going to do any of those by hand unless you're really good at math, right? I certainly wouldn't. So the easiest thing to do is to throw them in Excel. When you throw them in Excel, all you have to do is put your little up arrow there and 0.625. So that's how you show an exponent in Excel. And we'll look at it when we actually input the formula in a second. But you're going to divide that by width plus height, or width plus length if you want to think about that like that. But generally we're talking about ducts, so it's width and height, right? Even though when we do areas we say width times length, it's really width plus height for most of the stuff we do. And the exponent of, and actually I would put this whole thing in parentheses here just to be safe. So we'll basically write it out as if we're about to write out the formula in Excel. So times the exponent of, there we go, 0.25. So that's what we got going on. It's a pretty complicated little formula, right? Something you're not even going to be able to plug in the calculator very easy without messing it up. But we want to know what the equivalent diameter is. Let's go back to our 20 by 10 duct, all right? We had our 20 by 10 duct we were talking about earlier. And we wanted to use round instead of rectangular, or for some other reason we needed to know the equivalent diameter of it. When we do duct sizing, this is going to come up a lot, so it's a good way to be able to predict this stuff. We have a width of 20 and a height of 10. We can put this in Excel pretty easy, and you might want to watch a couple videos or practice it. If you don't want to do it, that's fine too, but I figured I'd just show you guys in case you've never done it before. We can go equals. You have to start with an equals, and as a matter of fact, let's go equivalent. Let's go ahead and just label this so that you can see it. All right. We can put this whole formula in basically and have two numbers here because there's only two numbers we got to change, and we can find the equivalent diameter of multiple ducts like this. So, oh, gotta switch back to Excel. All right, so we got this in Excel, right? We wrote width 1.3 times width times height. So basically, all I did was type this out so that you could see it. We just wrote width in one cell. I'll do it one more time real quick. We write width in one cell. Height in another. So 20 by 10. And now we want to know the equivalent diameter. Alright, so what we'll do is we'll say equals. You always have to start a formula off with equals. And then we basically copy the formula as I put it in. Most of the formulas I do, I'll try and write them out so that I can see how they're written out in Excel, so that it's pretty easy to just plug it in. There you go, 1.3 times, and then so that we can reuse this and just plug in numbers again later, we'll put the other parentheses and we'll just click on the cell that we want. Then use the asterisk for multiplication in Excel, and then you'll need to navigate to the other one. I'll have to use the arrows because it's covering it up, of course, but I'll show you guys this again where you can, sometimes if you go a space down, it makes it easier. But anyway, you have to navigate to the cell that height is in. Close the parentheses on that. Put your exponent, 0.625, and then divide it by the width again, parentheses, width again, plus your height to the exponent of 0.25. Typo. Where am I messed up parentheses. So type it up here. Closed it. So we should have closed the parentheses back here. What? Why is it yelling at me? Anyway, sometimes it's easier if you put the cell down here. Try this again, make sure we got it right. Equals 1.3 parentheses. Anytime you put a parentheses, you gotta close it. So 1.3 times width times parentheses, times height exponent 0.625 divided by parentheses width plus height exponent 0.25 15. There we go. Got it typed in right this time. So you basically just plug in all that stuff right here. So if you want to see how you do it, we can put an asterisk here, because that's how you multiply. Asterisk there, multiply. Asterisk there, multiply. You basically just plug all that information in formula here and just pick these cells, and it'll spit out an equivalent diameter of 15.23375 duct. So if you wanted to use a round duct, you'd round up, go into a 16-inch round. That's the same as a 20 by 10 duct, basically. So equivalent diameter is something that we'll have cheat sheets on later. You can basically keep a bunch of tables with you and do it, but I find it way easier to be able to plug something in so that I can automatically find it. So if I needed to know the equal diameter of a 10 by 10 duct, then we plug those numbers in and it'll change, and we'll go to 10.9 inch diameter duct. So architect's rule to engineer's rule. Architect's rule to engineer's rule. If you get decimals, all right, a lot of times when we're working with all this stuff, you'll get just like that. We'll have a 59, well, we'll have a 15.6 inch duct, okay? Excel's not really necessary for this, but it's going to make it a little easier to type out. What's 0.6 inches? I don't know, right? Especially when you get into feet, you're going to have a couple decimals to work with. You're going to have the decimal in feet and then the decimal in inches. So if you need to convert a number from feet to feet and inches in fractions, you need to know how to do that pretty quickly so that you know what kind of numbers you're working with. So say we're working on some kind of problem and we had 16.78 feet. How do we take that to feet and inches? Pretty simple. We know we have 16 feet, right? Done. We have 16 feet. We have 16.78 feet. We know we have 16 feet. Take the 0.78, all right? So take the 0.78, go back, look at the calculator again. You take your 0.78 and you multiply that by 12 to get the number of inches you have. So 0.78 inches is 9.36 inches. So now we know we have 9 inches. All right. Well, how many fractions of an inch do we have? Easiest thing to do is take 0.366 and multiply that times 16 for 16ths of an inch. If you don't need to know it to a 16th, you can just multiply it by 8 for eighths of an inch, or 4 for quarters of an inch if that's all you need to. But 16, generally how your tape measures are divided up, it's the easiest way to do it. So 9.36, so 0.36 times 16 gives us 5.7616. So we can either say we have 5/16, or we can round that up and say we have 6/16, because really it's closer to 6/16, right? You can either say you got 5/16, or if you'd rather round it up and be closer to it, 6/16 of an inch, we'll simplify to 3/8. Pretty simple. We'll do now. We probably won't practice it much more. So you may want to practice that a couple times and see what you come up with. I'll make a couple problems for it. We'll probably do some kind of a quiz on this lesson, but we can do some more examples in the next meeting too. But that's basically how it's gonna go. If we did another example, say we had 20.12 feet. We know we have 20 feet. 0.12 times 12. For how many inches we have would be 1.44 inches. So 1.44, we have 1 inch. And then take the remainder of that 0.44. Multiply that times 16. And we get 7/16 of an inch. So 20 foot 1 and 7/16. Pick that. Go to wants to automatically go to the date. You gotta format it as text and then fix it. So 20 foot 1 and 7/16. Was there anything else we were gonna look at? No, that's basically the gist of it. Let me know if you guys want to do a little bit more of learning some of these formulas in Excel. I don't want to work on it too much, but if you do a little bit of practice on it, if you haven't worked with Excel or Google Sheets or anything like that a whole lot, then if you need a little help with it, let me know. I will probably put a couple calculators up for you guys to play with at some point, but I want you to try and practice doing this yourself because it's a valuable thing to learn. And obviously, there's plenty of YouTube videos out there that can probably help you learn to put basic formulas into Excel. But where this is really going to help you with is when we get into complex equations, just like we just did equivalent diameter of duct. If you're trying to do, when I give you exercises on doing ventilation air into commercial buildings, if you can sit down, come up with a simple Excel formula and plug in those numbers, um, you'll be able to do that a lot faster than doing every single one by hand. And the other thing is if you are working on load calculations, when we talk about manual J, and we learn to do load calculations using the abridged edition, which you guys have, which is all done by hand. You don't want to actually do the whole thing by hand. It will take you absolutely forever. They have Excel speed sheets that you can use, and it's even simpler than doing this because most of it's already in there for you. You just have to change the numbers around. But being able to write those formulas yourself, you'll be able to notice where you're making errors easier, and you'll be able to know how to make basic formulas for stuff like equivalent diameter or something like that. And that will help you a lot instead of always doing it on a calculator. If you'd rather just do it on a calculator, that's fine, but I figured I'd cover it briefly so that you had an idea of what you're doing there. So that is pretty much all I want to cover on this one. If you have any questions, let me know. I will make up a short quiz assignment for you to apply this information, and we'll talk about it. But that is some basic trade math to get you started. Some of the things you'll have to do, some of the practical applications of it. Most of it we will cover in plenty of times this year. This is not information that you're going to be able to forget. You're going to be using all of this information multiple times. The only thing we probably won't do much of is area of triangles, area of pyramids, maybe not too much of the engineers to architectural, but It's still something important to know because there's times when you're going to need to know those inches or fractions of an inch, especially when you're changing from square inches to square feet and stuff like that. Um, and depending on where we go with VRF, we may not cover the gas pressure law again. So if any of those things you just don't get it, let me know and we'll talk about those more. Everything else we can cover again briefly, but we're going to cover it a few more times this year. So it's not a big deal. You just need to be aware of where your starting point is, whether this is easy for you or it's difficult. If it's easy, you're good. Difficult, you want to practice it some more. I want to make sure you understand it and ask me some questions. Otherwise, you'll get way behind when we start doing things involving math. So that's about it. If you got any questions, we will go over it.